Let's now do ketose family tree. So ketose family tree. Aldose family tree we have completed. We have done Killiani-Fisher reaction in which we gave KCN HCN in the presence of water, and after that we gave palladium PD Ba or BaSO4 in the presence of H2O again. Next we gave step down reaction we did, which was Ruff's degradation. In that we used bromine water oxidation method. Then we did decarboxylation with the presence of Fe2SO4 whole thrice and hydrogen peroxide H2O2. Okay, so CO2 and H2 we get as a byproduct in that. So that too we have done. Now we are going to see ketose family. So as we were starting in aldose with aldo triose, because aldo triose was CHO in the top and HOH CH2OH, so it was not having any plane structure. But what happens here, if you start with 3C in ketose family tree then you get CH2OH, then you get this one, and again CH2OH. So this you get a plane of symmetry over here, plane of symmetry. So as you get a plane of symmetry over here, you do not have any chiral carbon, no chiral carbon, isn't it? So also followed by no optical activity. So ketose family tree we do not start with 3C. This is not a carbohydrate according to modern definition. So we just start with 4C. 4C is CH2OH, C double bond O, you get HOH, CH2OH. This is your 4 carbon and we name this as erythulose. Okay, so now just keep on doing. Again same like that, only increase one center. Erythrulose 5 carbon we are getting CH2OH. Okay, C double bond O, just HOH, another center HOH, then we get CH2OH. Okay, so this is ribulose. Okay, next similarly everything same but CH2OH, C double bond O, OH, HOH, CH2OH, you get xylulose. Okay, similarly again I divide this to get 6 carbon sugars. Okay, so CH2OH, C double bond O, HOH, HOH, HOH. Psychose. Similarly everything will be same, only OH, H this side, HOH this side, HOH. You get CH2OH, CH2OH, C double bond O. This is fructose. Then you get over here CH2OH, C double bond O, HOH, OH, H, HOH, CH2OH. It is sorbose. Similarly, everything same, only this CH2OH, C double bond O, OH, H, OH, H, HOH, CH2OH. You get tagatose. So everything is same, only the difference over here is you start with 4 carbon, increase one center, and you need to remember the name. So over here I am just making a small chart of names so that you can remember it. You start with erythrulose, you go to ribulose, you go to xylulose. From ribulose you get psychose, fructose. From this one you get sorbose, tagatose. So this is ketose family tree. Okay. So next let's see stereoisomerism in monosaccharide. So what is the stereoisomerism in monosaccharide? Two or more molecule that have same molecular formula but different chemical structure. That is isomerism, isn't it? What is stereoisomerism? That two or more molecule that have similar same formula, same molecular formula but different chemical structure. So that is called isomer. So I have taken an example like C2H6O. So if you divide at C2H5OH, you get ethanol. But similarly, if you do this as CH3OCH3, then you get dimethyl ether. So they are constitutional isomer. They are called constitutional isomer. Okay. So over here, what is isomerism? You need to remember two or more molecule have same formula but different chemical structure. Then I have give you an example of constitutional isomer. Okay. So what are the types of isomer? You have constitutional isomer, which is not needed for your this one. So I have just crossed it. Then I have stereoisomers. Yes, it is needed. This is called stereoisomerism, that whenever you are drawing the structure, OH this side, HOH this side, so this is continuously rotating. So 3D structure need to be seen to differentiate rotation around single bond. So over here you have the question, same connectivity of atoms. Do they have same connectivity of atoms? No, constitutional isomers do not have same connectivity of atoms, but stereoisomers, yes, they have same connectivity of atoms. Now we have conformational. Rotation around single bond. Yes, but you do not have conformational. Configurational, no, not rotation around single bond. Okay, so HOH, OHH. So this is your configurational isomer. No, you do not have conformational. Okay, you have configurational. So what you have? You have stereoisomers. So this one, stereogenic center change. Then you have configurational isomer, nothing, just OHH, HOH, this thing is changing. Okay. Then from this you have optical isomer, geometrical you don't have, optical isomer you have, which is mirror image. From optical isomer we have the concept of enantiomer and diastereomer. What is enantiomer? Non superimposable mirror image. You get the mirror image but it is non superimposable. Okay. And what is diastereomer? No mirror image is formed. No mirror image is formed. If I say enantiomer, if I say what is enantiomer, show me an enantiomer. So I told you in the very first class, those who have not seen my notes of my first class, over there when I was drawing aldose family tree, I told that every structure As you go d-erythrose, d-threose, then you go d-ribose, okay, d-arabinose. So that way everywhere d is written, d. So how the d is coming, what is that d? I told you do not write now, but in the books you will see it is written d. I will explain as I go ahead. So I went ahead, I am telling you why just d. When in this kind of single bond you have OH in the right side, then it is D-glyceraldehyde. When you have OH in the left side, then it is L-glyceraldehyde. Okay, ma'am, I understood it. But what if this is not having only one? Like you have many more carbons. Not it is a 3 carbon. If you have 4 carbon, 5 carbon, then what to do? Okay, no problem. Your ma'am is here. Let's see. Okay. So, yes. Chalo, let's check it. When you have like this, you need to check the penultimate carbon. What is penultimate carbon? The carbon before the last carbon is called the penultimate carbon. So this is a 6 carbon structure, you need to check the 5th carbon. If the 5th carbon is having OH at the right side, then D. If OH at the left side, then L. For single OH at the right side is D, OH at the left side is L. But when you are having this one, more than 3 carbon, then you need to check the penultimate carbon. Penultimate carbon is the carbon before the last carbon. Okay, all naturally found sugars are D in nature, L not found. Example, D glucose, L glucose. In L glucose only penultimate carbon change. So nothing. This is the D glucose structure. If you need to draw the L glucose structure, go OH here, H here. Okay. So this way question can come, draw that L glucose. Then you will draw that like that way. Okay. Now you have a diastereomer. You understood what is enantiomer? Enantiomer is nothing but you need changing the position D and L, capital D and L. But in the first class we did optical activity. Okay, small d and small l. Do not mix with that. That was dextro. If it rotate to the right side, then it's dextro. If it rotate to the left side, optical activity. Okay, so that was levo. Do not mix with that. This is capital D, capital L. Now we have diastereomer. No mirror image relation. Okay, multiple chiral carbon change. Okay, so no mirror image relation. So example, glucose versus mannose, allose versus glucose, glucose versus galactose, D-glucose versus L-mannose. So there is no mirror image relation. They do not form mirror image. So anything, just do anything. Okay, compare any structure with any structure. That is a diastereomer. Okay,